Okay, we're going to review the SN2 reaction now. Here's a typical SN2 reaction involving a nucleophile and an electrophilic substrate which contains a leaving group. This is called an electrophilic substrate because the leaving group is going to be more electronegative than the carbon. So there's going to be a bond dipole moment moving toward the leaving group, making that carbon atom somewhat electrophilic. So our nucleophile simply comes in and attacks, always in the same direction, always from the back of the carbon leaving group bond, and the two sigma electrons associated with this bond wind up on the leaving group. So we produce a new carbon nucleophile bond and also a leaving group anion. The aeroformalism for an SN2 reaction is quite simple. It's a concerted reaction because this bond making step and bond breaking step are occurring at exactly the same time, which is what concerted means. The requirements for an SN2 reaction. We have to have a good nucleophile. We just saw that nucleophile approach from the back of the carbon leaving group bond. It has to be a good nucleophile. Weak nucleophiles will not work in an SN2. We have to have a good electrophilic substrate. We'll talk about what that means in just a moment. Got to have a good leaving group. As far as the solvent goes, we're not too fussy. There are examples of really good SN2 reactions that occur in either polar or nonpolar solvents. So let's talk about nucleophiles. We said we've got to have a good nucleophile. It turns out there are lots of potential nucleophiles which we could use, and they're not all good. Some of them are truly excellent, like the cyanide anion, the thiolate anions, iodide anions. Those are excellent nucleophiles. Those will always be good choices if we're trying to run an SN2 reaction. Others, like hydroxide, alkoxide, bromide, and the various amines. So this is ammonia, the simplest of all amines. This is a primary organic amine, a secondary amine, a tertiary amine. All of these are good nucleophiles, and we can use these for SN2 reactions as well. As we look at the rest of the list, we're getting down into weaker nucleophiles. Chloride is not as strong as bromide or iodide. It's only fair. We might be able to get away with it as a nucleophile in an SN2 reaction, but it's not going to be as good as these up here. This is called a carboxylate anion. Because of the resonance delocalization of this negative charge, neither of these oxygen atoms bears a full negative charge, and therefore it's not as nucleophilic. And then we get all the way down here to the poor nucleophiles. Water and alcohols are poor nucleophiles, and they're going to be unacceptable as nucleophiles in SN2 reactions. So if you're trying to run an SN2 with water or an alcohol as your nucleophile, that's a bad idea. What about electrophilic substrates? The smaller and less substituted substrates are the best. So methyl substrates and primary substrates, they're the best. They're better than secondary substrates, which in turn are much better than tertiary substrates. And tertiary substrates are so bad, we just cross them off and say you can't use them in an SN2 reaction. Now why is this? It has everything to do with steric hindrance. Remember, the nucleophile has to approach the back of the carbon leaving group bond. If this is just a methyl group, these little tiny hydrogen atoms don't provide any significant steric hindrance to the nucleophile. The nucleophile can get in there, form a new bond to that carbon atom, displace the leaving group, not a problem. But if we start replacing these hydrogens with organic groups, if we replace it with one organic group, this carbon becomes primary. With two, it becomes secondary. And if all three are R groups or organic groups, then this carbon is now tertiary. These organic groups take up more room, and they block the attack of the nucleophile. The nucleophile simply can't reach this carbon, can't get to the back of it in order to displace the leaving group. So it has everything to do with steric hindrance. The SN2 reaction is sensitive to steric hindrance, and that's why we see this reactivity ordering as shown. Let's talk about leaving groups. We're going to categorize them as in just two ways. They're either good or they're poor. So the iodide, the bromide, and the chlorides, most of the halide anions are good leaving groups, and water is also a good leaving group. There are other examples of good leaving groups like the tosylate anion, TSO-. Tosylate is a good leaving group. and plenty of other examples. There are also some poor leaving groups, the fluoride anion, the thiolate anion, and the cyanide anion, all examples of poor leaving groups. Notice that fluoride is the only halogen that's a poor leaving group, and that has everything to do with the strength of the carbon-fluorine bond. It's such a strong bond, it's so hard to break that fluoride anion becomes a poor leaving group. These two are interesting. Thiolate anion and cyanide anion were both examples of really excellent nucleophiles, but they're poor leaving groups. And finally, hydroxide, OH, is a lousy leaving group, and so are alkoxides. So for example, methoxide, OCH3, or other alkoxides. These are all poor leaving groups. So let's look at some example SN2 reactions. Here's one where our thiolate anion, which we know is an excellent nucleophile, it's on our list as one of the best, is going to approach this electrophilic substrate. As we examine this substrate, the carbon that bears the leaving group is secondary. It's attached to two other carbons, so that's a secondary substrate. They're not the best for SN2 reactions, but they're acceptable. And we have an excellent nucleophile, so we expect that we should be able to run an SN2 reaction here. Because the leaving group is in front, and because our nucleophile has to approach from the back of the carbon leaving group bond, this literally means that this thiolate anion must approach from the back, from behind the plane of the paper, coming in behind, knocking off the leaving group. And that's why we show that it's formed here. The new carbon-sulfur bond is formed in the back. In this particular case, we started out with a reaction center, a carbon atom, which was a stereogenic center. It's 100% S. That's what we started with. 2-iodopentane, in which the stereogenic center is 100% S. Because of the requirements of the SN2 reaction, the nucleophile coming from the back, we wind up with a product which is 100% R. This is an example of inversion of configuration. And the way we can sort of think about that is that the reaction is actually stereospecific. Every SN2 reaction is stereospecific. It always occurs with this inversion of configuration. Sometimes we write 100% inversion of configuration. So in this case, we're talking about the S configuration being inverted to the R configuration. And as I mentioned earlier, this is a concerted reaction. That's also a very important thing to note here. This arrow formalism indicates we're forming the new bond to sulfur using this lone pair right here. We could just as easily have used one of these two lone pairs. We're forming a new bond to sulfur, and we're breaking the bond to the leaving group, and those things are happening at exactly the same moment. It's a concerted reaction. Here's another example of an SN2 reaction. We have another really excellent nucleophile. This is our cyanide anion approaching this electrophilic substrate. Once again, it's a secondary substrate. The carbon that bears the leaving group is attached to two other carbons, so that makes it secondary. Not the best, but it's acceptable. And once again, we have a very good nucleophile, and we've got a good leaving group. So, because our leaving group is in front once again, the nucleophile must approach from the back. Literally, it would be coming from behind the plane of the paper, knocking off the leaving group, and in this case, we would form the following molecule in which our new carbon nucleophile bond is in the back. We started out with 100% S, we wind up with 100% R, and of course we've knocked off the leaving group, so we'll indicate that as well. Notice that our bromine atom started with 3 lone pairs, and when we displace the leaving group, these 2 electrons of this carbon-bromine bond go with the bromine. That's what this 2-electron arrow indicates, which gives us now a 4th lone pair on bromine and consequently a negative charge. Notice that both of these reactions, top and bottom, are shown as equilibrium processes. In general, every reaction is, at least in principle, reversible, but in practice, this is not always true. Both of these would be examples where reversibility is limited. Can we understand why that would be true? Well, it has to do with the cyanide anion and the thiolate anion as leaving groups. So if we think about the reverse reaction, bromine would have to come now from the front, displace the cyanide anion as a leaving group, and we know that that's just not a very good leaving group. So consequently, this equilibrium is going to favor, quite dramatically, the product shown on the right. The same would be true here because the thiolate anion is a poor leaving group, so if the iodide came in to displace it, it's going to be more problematic than the forward direction. Okay, here's another one. Here I'm using an alkoxide, in this case it's a methoxide anion as my nucleophile. I've got a primary substrate, so this is a particularly good substrate. It's primary and my leaving group is a really good one. It's going to be the iodide anion. So my nucleophile comes in from the back of the carbon leaving group bond, displaces the leaving group, there's my product plus the leaving group anion. But we have to note here that in this case, because we chose a nucleophile, this alkoxide nucleophile, which is also a strong base, this SN2 reaction is going to actually be in competition with an E2 reaction. E2 and SN2 reactions are frequently in competition, especially when we're using either hydroxide or alkoxide anions as nucleophiles or bases. So this is our abbreviation for nucleophile, this is our abbreviation for base. In an E2 elimination, we're using the alkoxide as a base. How does it happen? We're going to talk a little bit more about E2 in a different video, but notice that this is the carbon that bears the leaving group. One carbon away is an alpha carbon. And as long as we can place one of the hydrogens in an anti position, anti means that if we were drawing a Newman projection looking down this carbon-carbon bond axis, the leaving group and the alpha proton that we're trying to pluck off with our strong base would have a 180-degree dihedral angle. So this is an anti-conformation, anti with respect to this hydrogen and this leaving group. As long as we can get one hydrogen in an anti position, we're going to be in great shape for an E2 elimination if we have such a strong base like this. The base will come, pluck off the proton, literally. This hydrogen atom will leave as a proton, as an H+, because these two electrons get kicked over to form the new pi bond, and at the same time we lose the leaving group. The result in this case would be a 1-butene, and that would be an E2 product. So this particular reaction would form both an SN2 product as well as an E2 product. Let's wrap this up by looking at a couple of different electrophilic substrates and ask the question, which will react fastest in an SN2 reaction? So part A, we've got 3 substrates we're going to compare. This is a primary substrate. The carbon that is attached to the leaving group is primary. This is a primary substrate. This is a secondary substrate. We know that primary substrates are better. Which of these 2 primary substrates will be best? Well, it turns out this one's not good at all because this is an alkene. This carbon right here, which is attached to our leaving group, is sp2 hybridized and trigonal planar. That's not going to work for an SN2 reaction. An SN2 reaction is going to require a carbon that is sp3 or tetrahedral. So of the 3, we can rule out this one immediately because the leaving group is on an sp2 hybridized carbon. And of these 2, the primary substrate is going to beat the secondary substrate, so that would be our top choice. Let's look at B. In this case, we have a lot of similarities. They're all 2 halopropanes, where the halogen atom is the only difference, chlorine, bromine, or iodine. So in this case, we need to go back and look at our leaving groups, and we realize that the iodide is actually the best of the 3 leaving groups. Bromine is, bromide anion is also a good leaving group, but iodide's the very best. Where halogens are concerned, the abilities of the halogen atoms to behave as leaving groups is a function of their size. Iodine is the biggest, and it's the best leaving group. Bromine is next biggest, and it's second best leaving group. Chlorine is next biggest, or next smaller, I guess, and it's not as good a leaving group as these first 2. And fluorine, which is the smallest of all, is the worst of the leaving groups. So that's an easy way to remember. If you remember the way the halogens are located on the periodic table, it looks like this. Iodine's your best leaving group, followed by bromine, followed by chlorine, followed by fluorine. So our winner here is simply the one that has the best leaving group. Let's look down at C. Here I have a bridged bicyclic, here I have a cyclic, and here I have a tertiary butyl bromide. Well, if we're talking about an SN2 reaction, this is a tertiary substrate right here. The carbon that bears the leaving group is tertiary. We can just cross that one off immediately. We know that SN2 reactions don't work at tertiary substrates. In fact, this is also a tertiary substrate. This bridgehead carbon is attached to the iodine, and it's also attached to 3 other carbons. It's tertiary. We can cross it off. It's interesting to note that even if this were not a tertiary substrate, we'd have serious problems with this one, because the nucleophile has to approach from the back of the carbon leaving group bond, and in this case, the back is somewhere in the middle of this bridged bicyclic structure. That would be really hindered, highly sterically hindered. Our nucleophile could never get back there in order to form the bond. And even if it did form the bond, it would be poking into the other side of the bridged bicyclic. So this one's got all sorts of problems associated with it. The only one that's acceptable is this one. Notice that in this case, the chlorine is not the best leaving group. Iodine and bromine are better leaving groups, but it's the best substrate overall because it's secondary, it's not tertiary, and it's certainly not part of a bridged bicyclic system. So this is a case where you have to weigh a couple different factors. The bromine, the chlorine, and the iodine are all acceptable leaving groups, not so much the fluorine, but these 3 are all acceptable leaving groups. If we have to choose between them, all else being equal, we'd choose the iodide. But if all else is not equal, we'd choose whichever one has the best electrophilic substrate. Secondary is going to beat tertiary. It's going to beat the bridged bicyclic. Finally, we go down here to this last example. I have an alcohol, a bromide, and an iodide. Alcohols, if they're going to react in an SN2, would presumably have this OH group as a leaving group, and OH is a lousy leaving group, so we're just going to cross that one off. No chance for that. Bromide and iodide, both acceptable leaving groups. Iodide, again, is the better leaving group, but let's look carefully. It's on a tertiary substrate. The carbon attached to the iodine is tertiary, whereas this bromine is secondary. Tertiary substrates are so sterically hindered we can just cross them off. They won't react, which means that that's our best choice. Okay, I hope you enjoyed this review of SN2 chemistry. Look for a review of SN1, E1, and E2 as well.